typically you would have the most important, one important capacitance in a device, a BJT or MOSFET, okay, one. And then depending on how many you have externally, right? For example, if you have two externally, then you totally have three capacitors. And then you're going to have three corner frequencies, right? Okay. All right. So again, let's focus on the external first. Okay. So I'm going to do an example here. Okay. So for this amplifier, we know A sub B max is 10. The two corner frequencies are 200 first and 3K first. We know the Q point is located in the middle of DC. All right. So R1 plus R2 is 225K. Okay, that's what we know. Oh, we know VTN, the threshold voltage of the MOSFET, is 1 volt. Kn is 80 microamp per volt squared. So now we have to design the circuit. Design the circuit means we have to find all this. Oh, this one is given, by the way. This one is 200 ohm. So we have to find all the unknown parameters, components. So basically, we have to find RD, R1, R2. What else? C1, C2, right? So that I can get all this performance. So how do we start, huh? Okay, well, you may want to start from the DC, huh? See if you can get something out of the DC analysis. So if you look at output loop, right? Under the DC, 9 volt equal to IDQ RD, yes, plus VDSQ, right? Well, you know what is VDSQ, yes? It is half, right? It's 9 divided by 2, so it's 4.5 volt, correct? According to the to this information, right? Now the question is, what is IDQ? Yes? That is a known, because if this is known, then you can find the value of R sub D. So we are not going to make it here. Okay, so let's see if we can try to get something out of A sub V max. Okay. To do that, you have to do the AC analysis, right? Okay, so let's do the AC. Basically, you have R sub S, R1 in pair with R2, right? Maybe I take out the R sub S, make it easier, okay? Just make it a short circuit. Okay, so we don't have any R sub S, which is okay. Okay, what else? So this is connected to the drain terminal, right? I'm sorry, the gate terminal. And then the source is grounded, yes? Source is grounded. And then the drain is connected to R sub D to the ground, yes? And that's your V sub L. So this is V sub I. Now, of course, if you want to put a capacitor, right? This is C sub 1 here. And this is C sub 2, right? C sub 2. Okay, then the model, we have a current source, right? GM VGS. So this is VGS. Okay, so that's it. So V sub O is equal to minus GM VGS R sub D, correct? Now, when you do this, right, you assume this is short. This is open, right? That's the shortcut. Okay, what else? V sub I is VGS, yes? Right? V sub I is here, which is the same as here, huh? So that makes it easy, right? So A sub V max is equal to minus G sub M R sub D, right? So that is given. The value of that is minus 10. So this should be a minus 10. All right. Now we also reach a dead end. Why? Because G sub n is a function of I sub D, right? So what is G sub n? G sub n is equal to 2 times square root of Kn IDQ, right? So IDQ is unknown. What do we do? Well, let's come over here, okay? There's an equation for IDQ, correct? So IDQ is equal to what? 9 minus VDSQ over R sub D, correct? And we know VDSQ is supposed to be half of the 9 volt. Yes? Because the Q point is located in the middle. now if you put this here, you get Gm equal to 2 times square root of Kn times R sub P 4.5. Yes? Then, let's call this equation 1. This is equation 2. Right? It's a little tricky, I think. So now if you put 2 into 1, so you get 10, which is A sub E max, right? Equal to GMRD, yes? And GM is right here, 2 times the square root Kn times 4.5 over R sub P times R sub P. So finally, I got one equation and one unknown. Yes? And the unknown, of course, is what? Is R sub P, right? So let's solve for this equation. It will be a quadratic equation, I think, right? I'm not sure. Maybe, well, yeah. Basically, you take the square root of both sides, yes? So 100 equal to 4 times Kn 4.5 RD, right? Times RD squared. Oh, it's not quadratic, yeah? So RD cancel, right? So you get R sub B and N, you get about 20 KO. Okay? So once you know RD, you can find IDQ, right? So IDQ, if we go from here, right? Because R sub P now is known. So IDQ will become 0.2 linear. Okay, and then we know IDQ, there's a formula, is equal to, I forgot, Kn squared times VGSQ minus VTN to the, is it Kn squared or Kn? Huh? Kn, right? Kn times VGSQ minus VTN to the power of 2. So from here, there's only one unknown, right? So that's the unknown. So VGSQ will become 1.8 volts, right? Okay, so if you come back to the circuit, so this is VGSQ, yes? Which is the same as the voltage drop here, yes? VR2, right? So basically, VGSQ is the same as the voltage drop on R sub 2. Yes? Okay, and there's a formula for VR2 is what? It's 9 volt times R1 plus R2 and then R sub 2. Yes? And this is known. Huh? Is it known? It's yeah, 225K. So therefore, R2 can be calculated, right? So R2 is 45K, and then R1 become 180K. All right. So we have found the values of all the resistors, right? So now we have to try to figure out the capacitors, huh? Erase this. Okay, so for the capacitance, if you focus on C1, huh? So if you focus on C1, On this side is short, right? Because when you do this, the equivalent circuit, this is short. On the other side, what do you have? R1 in parallel with R2, correct? So that is tau associated with C1. So it's C1 times this plus that, right? Actually, plus 0 if you like. Yes? Okay, and omega C1 is equal to 1 over tau C1, correct? So it's equal to 1 over C1, R1 in parallel with R2, correct? Okay, and this is in the unit of radian per second, but the frequency we got was in hertz, correct? So two corner frequencies were given, 200 hertz and 3K hertz. So if you want to convert this to the frequency, yeah? Frequency in hertz, then it's what? It's 1 over C1 R1 in parallel with R2 times 2 pi, correct? Yep. Because omega is equal to 2 pi f, right? It's 2 pi f on the other side. Now, but here's the problem. You are given two frequencies. So which one is associated with C1 and which one is associated with C2? Huh?
The series capacity. The one in series is the first, is the lowest one.
Yes, it must be the smaller one, right? Remember that this is a series capacitance. The series capacitance always introduce a corner frequency in the lower frequency range. Yes, the parallel always introduce a frequency in the higher frequency range. Yes, so therefore this is 200 hertz, right? Okay. Now of course you know R1 here R2, right? Because you know R1 R2, right? So by C1 is about equal to 0.02 microfarad, right? Okay, the same concept. Now we try to find out what is the time constant for C2, right? So now you have to do the find R out. Yes. So this is short. When you put a so basically this is that, right? Okay, so you put a test voltage, right? V test. So you have I test. Yes. So this is VGS. This is G and VGS, right? Okay. So what is I test? So I test, right, is equal to, there are two currents, huh? This one and this one, correct? Is equal to V test over R sub B plus GM VGS, correct? But VGS, we know, is what? VGS is 0. So therefore, IP is VT over R sub B, and R out is VT over I sub T, right? So it's R sub T. Right, so therefore if you focus on C2, yes? This is R sub out on the left hand side. On the right hand side, it's open, right? So it's like infinity, yeah? So tau associated with C sub 2. Tau C sub 2 is equal to C2 times these two are in parallel, right? R out in parallel with infinity, so equal to C2 R out, which is C2 RD. Yes? Okay, then omega C2 is 1 over tau, so it's 1 over C2 R sub D. And then FC2 is 1 over C2 RD times 2 pi, correct? And this is given. What was the value? 3K, yes? 3K. Right? So therefore, C2 is about 3 nanofarad. Yes? You know what's the polypar look like, right? Polypar should look like this. If you look at the frequency, right, in hertz versus A sub B, you have a plateau. What is the magnitude of that plateau? Huh? 10, that's a 20 dB, correct? Yes? 20 dB, so that's what we call the A sub B max, right? Okay, then you have a drop here, you have a drop here. So this is 200, yes? And that's 3K. The slope, I don't know if you look this way, it's plus 20 dB, right? Per decade, and this one's minus 20 dB per, yes? Okay? Question? All right. Let's do one more example on the subject, and this time we're going to have 3 capacitors. Okay.
I don't know, I was writing something down, I don't know if I missed something, but where you have the hash mark on the Y, the AV accents, and it says, is that 20 dB?
Yeah.
Because I thought our AV max was 10. Am I getting
10,
something wrong?
10 is the real number. You have to convert this to dB, right?
Yeah.
So you take the 20 log 10 of 10,
Yeah.
which is 1, I think,
Yes.
and then multiply to 20, that's why you get 20 dB. Okay. Okay, I will do this one as comprehensive as possible, right? So that's quite comprehensive, huh?
Whether it's two RS behind capacitor.
C1, oh, use C2, call it C3, right?
I think it means the source resistor and the RS in
Huh?
front.
R sub X?
Yeah, there's another one at the MOSFET too. They're both R sub S.
Oh, yeah.
Yeah.
So let's call this R sub X, huh?
Yeah.
Yeah. All right. I'm not sure I have all the numbers. Okay, so let me just give you the expressions, huh? Which are more important than numbers. Okay. So basically, I want to find out the body plot. Yes. And you should know what is the plot going to look like. Yes. I hope. Huh? You have 3 capacitors, right? So, and you have 2 in series, 1 in parallel. So you should have 2 chorus frequencies in the lower frequency range, and 1 in the high frequency, right? 1. So therefore, you should have a plateau, which you say is a Vmax, right? You should have 1 here, the second one, right? Okay. I don't know which one is associated with which, depends on the numbers, right? And then you have 1 in the higher frequency range. But I know that must be associated with what? C3. Yes? C3. This one is omega C1 and omega C2, right? The location of that depends on the values of tau. So the slope minus 20 dB per decade. This slope, if you go this way, is plus 40 dB per decade, and this is plus 20 dB per decade. Yes? Now, when you look at this number, it looks good, huh? Plus. Actually, it's not good, huh? Because basically you are focusing in the bandwidth, right? Anything that is dropped, that's not good. Ideally, you want this to be like this, huh? Ideally. But because of the capacitors, so it'd be nice we can invent something that can serve as a capacitor, but it does not have the effect. Huh? Okay. So how do we get started? I think the best is to try to do the ASV max first, right? Okay. Oh no. The first thing you have to do is what? It's the BC. Okay, let's skip the BC. Huh? By now, if you don't know the BC, I don't think you should get a passing grade. Huh? Huh? I don't want you to advance to the next class, and then you tell the professor, oh, I took Professor Lu's class, and I do not know how to do the DC analysis of that, right? And I got an A. That's called the, we have had some professor who inflated the grade. Yeah. And that was a problem. One of the professors, I remember, he gave more than 80% A and Bs, undergraduate class. So when it came up for application, for promotion, something, and that became a problem. Now, of course, you can argue that. You say, oh, I got a special class, and then most of the students are very smart people, right? I've not seen that in the past 30 years. Right? I give you an example, right? If every one of them could get 90th and 100th, then I would have no problem. I can go to talk to the university, anybody, right? I said, I can give 80% or 90% A's in the class. If you can show me on the exams. again, I'm not seeing it. So, okay, so basic analysis, you know how to do it, right? So I'm going to skip it, okay? So now I'm going to go to the AC. Actually, we have done that many times, but I'm going to do this one more time. Yes? Okay. The source has also S to the ground. Yes? The gate, of course, is open. The drain, I have an R sub D to the ground. Yes? And then I have a C sub 2 in series. And then I have an R sub L to the ground. Yes? And then I have a C sub 3 in parallel. So that's E sub L. Okay, so here's the current source. Right? Right, so the first thing we're trying to find is A sub B max, right? So in doing that, your C sub 1 is short, yes? C sub 2 is short. C sub 3 is open. Right? Okay, so what is V sub L? V sub L is minus G sub N VGS, right, times R sub B in parallel with R sub L, right? Okay. Now, what about V sub I? Huh? So you need to try to find the expression of V sub I as a function of VGS. Yes? Okay. So this voltage, okay, this voltage right here, huh? This voltage is VGS plus that, which is GM-VGS times R sub S, correct?
Mm-hmm.
That's the voltage. And that is across this. And this is a portion of that. Got it? So therefore, this is the voltage across R1 in parallel with R2, correct? Okay, and that VR1 in parallel with R2 is V sub I according to the voltage divider rule. And then R1 in parallel with R2. Correct or not? All right? So therefore, if I put this here, right? So I get 1 plus GM RS VGS, right? Equal to V sub I R1 in parallel with R2, R sub I plus R1 in parallel with R2, right? Okay, and I can put V sub I on one side, so V sub I becomes times okay. So basically, I rearrange the equation. Yes. So I get V sub I on the left and everything else on the right. Okay. So that will allow me to take the ratio because it's a function of VGS, right? So therefore A sub V max now is equal to what? Is equal to this on top, right? So minus GM RT imperials R square, correct? This is on the bottom. So Ri plus R1 imperials R2. Yes? Times 1 plus GM R sub S times R1 imperials R2. I hope I'm doing this right, huh? Yes? It's algebra, okay? There's nothing tricky about it. Okay, so you can plug in the numbers and get values. Again, I don't have the numbers. So. Any questions about this? No, we have done this before, right? So, okay. So now let's go to find the corner frequency, right? Tau C1 should be fairly simple, right? It's what? C1 times Ri plus R1 times R2. Yes? Correct? So omega C1 is 1 over that. Yes? So that's one of the corner frequencies. Okay, C2. To do C2, let's do the family. Yes? Like this. Okay, so you can looking for R out. Alright, so you put a B test and I test, right? So this is GM VGS, right? And here's VGS. Okay, so if you look at this node, right? I test equal to V test over RP plus GM VGS. Correct? Okay. And this voltage is what? VT, correct? So and this is this plus that. Huh? So it's VGS plus that. What is that? GM VGS RS. That equal to VT. Yes? Well, there's only one solution for that. Is it or not? What is VGS? So VGS is equal to VT over 1 plus GM R squared. Yes? Is it? So then you put this here. Correct or not? VGS, let me double check.
So,
Yeah, huh? Correct? Okay. So you put it here, and then you divide this and R out is equal to VTIT, right? So it's equal to 1 over R sub P plus 1 over that, yes? So it's GM 1 plus GM R sub S minus 1, I think. All right, so now if you look at C2, right? So C2 on this side you have R sub out. On this side, you have R sub L, correct? So therefore, tau C2 is equal to C2 times these two in series, yes? R out plus R sub L. So omega C2 will be 1 over this. Yes? Okay, finally, for C3, what do I have? So for C3, that side is open, right? Nothing. On the left hand side, you have an R sub L, yes? And then what else? Out, right? Because everything from here is R sub out. Yes, we have found that. So this is C3. So tau C3 is C3 times, right? This in parallel, this is open, so it doesn't matter. So it's R out in parallel with R sub L, yes? So omega C3 is 1 over tau C3, so it's C3 R out in parallel with R sub L. Yeah? So let me just give some random numbers to make it easier to visualize. Okay. So let's say after this, let's say you get this like 50 radian per second. Okay. Oh, this cannot. This must be high. Huh? Let's say 10 to the 7 radians per second. Okay, and this one I can assign a number. Let's say it's 100 radian per second, right? And then there's one more right here, right? That's 50. 50 radians per second. Okay, so now we can sketch the plot. Then, so this is A sub B versus omega, right? Okay, so we have 3 corner frequencies, 50, yeah, so there's a 50, there's a 100, and then there's a high one, 10 to the 7, correct? So between here and here, okay, the first drop, you have a constant, which is A sub B max, yes? Okay, between here and here, it's a 20 dB per decade, yes? And below 50, 40 dB per decade. Yes? And beyond 10 to the 7, minus 20 dB per decade. Huh? So again, let me give you a number, okay? Make it easier. Let's say this is 20 dB, huh? So the question is, what is A sub B at 50 omega equal to 50? What is it?
14.
Good. Yes, because it dropped by an octave, right? 100 to 50, a factor of 2. So therefore, this is 20. So that must be 20 minus 6, right? Okay, so it's 14 dB. Okay. Now, if I want to find out what is A sub B at omega equal to 10? Oh, you say 10, that's easy, yeah? 100, right? You drop by a decade, correct? You cannot do that because there are two different slopes. If you only have this slope, then that's one decade drop. It's easy. But then you have two different slopes. What do you do now? So at 50 we know it's 14, correct? So if I do one decade, so I will get to 5. Yes?
Mm-hmm.
And then I can go backward by one octave. That becomes 10. Got it? So let me do that here. So here is 50, right? I know it's 14 dB. Yes? Okay, then we have a slope. How much? 40, right? 40 is equivalent to how much per octave? 12. Yes. Okay. All right. So if I go to 5, then what is it? If I go to 5, it's minus 30 minus 26. Agree? If I go to 5, that's one decade, right? So that means I would drop by how much? By 40. So 16 minus 40 is 26, minus 26, right? Okay, then I go back up. So this is 10. So now from minus 26, I go back up by how much? This is one octave, 12. So therefore, at 10, right, that's this right here. What do I get? Yes?
Mm-hmm.
So somehow, if you have a experiment, right? You build a circuit like this, and in the lab, if you have this, what we call the spectrum analyzer, you can actually see this type of curve. But you told me you don't have. So. All right. Now there's a capacitor that I have not talked about, which is the bypass capacitor. Yes. Still have time. Good. Okay. So now let's talk about the bypass capacitor. Okay. So for example, we have something like this. Right? So you should know that that's a bypass capacitor. So we go to the AC analysis, right? So this is what you have. R sub pi, yes. Beta I sub B, I sub B, right? R sub E, yes. And then you have R sub C, right? That's a bypass capacitor. And then this is R sub C to the ground, yes? Right? Then what do? Then you will say, okay, if I use the shortcut, I use the shortcut. Then I can look in this side, call this RR1, can I? Then I can try to look the other side. I don't know how to do that. But they're both sides, right? Correct? So if you look at the other side, then there's RR2, yes? Yeah, but this RR2 could be difficult to find, I think. Correct? How do you find? You know, go this way is easier. Huh? You put a test voltage. Yes, this is short. That's what we have done all the time. Yes, but to this side, it becomes like this, and then I'm not even sure. Like this. Is it? No. Like this. Yes? Can you see that? This is in series, right? So if you take this out, look at the other side, that's what you have. And then you can say, okay, I put a test voltage here, right? We test. This is my test. Yeah, but then what is I sub B, huh? I sub B actually is on the other side, so it doesn't work. Okay? So you cannot use the shortcut to figure out the corner frequency associated with a bypass capacitor, okay? Cannot. So what do? You have to make it, this is 1 over SC, yes? So now you have to solve the whole circuit using the conventional approach, okay? And in the end, you're going to find that it does not introduce just one corner frequency, it introduces 2 corner frequencies. Okay, omega 1, omega 2, like this. So as far as the bypass capacitor is concerned, the shortcut does not work. You can see it has it's 2 corner frequencies. So let's not worry about it. Okay, let's not worry about it. Yeah.
Why I sub B just be negative B test over R pi?
You mean this one?
Yeah.
This one, what you saying? You say I test is what?
Or sorry, it's B test is whatever you set to be, and then I sub B with
I test must be equal to minus beta ID, right? According to that. Okay? Then now the question is, what is this, right?
Wouldn't that just be B test over R pi? Since
B test over R pi.
because there's no multiple sources on the left side, right? But you're because B test that node.
Yeah, but
The B test
but
is
you're
on
looking to
RE.
the right hand side. You're not looking to the left.
But the right hand side is still dependent on one.
It probably is. I'm not sure. I have to.
In that case,
Okay, even that is the case. Okay, then you should end up with a capacitor, right? And then you have one here, correct? According to the shortcut. So you're going to have one corner frequency, correct? Associated with that. But that is what you should have. So the shortcut does not work. Okay. Now there's an example in the book that talks about how you can solve the Bode plot for the bypass capacitor using the conventional approach. Okay, so you are welcome to take a look. So again, the shortcut will not work for the bypass, right? And because of that, I will not give you any problem in the exam that has the bypass. So you would see two capacitors, the series, the parallel, and maybe the internal. Yeah. Okay. Any questions? We still have 10 minutes. So let me introduce the concept of the internal capacitor. What? Okay. So I will introduce the concept today, and on Wednesday, I will do an example for the BJT circuit. On Monday, I will do an example on the FET circuit, including both the external and the internal. Okay, so I will do two examples. So that becomes quite important, I think, as far as the exam is concerned. And then on Wednesday, I can do maybe one more example, okay, which is probably closer to what you will see in the exam. Yeah. So let me introduce the concept. But we don't have time to do the example today, okay? Okay, we have to do both, right? We have to do the bipolar and also the FET, yes? Okay. So, BJT model, including internal capacitors. Now, as you know, in the past, we have used this model, yes? This is R pi, correct? You can call this V pi if you like. This I is a B, yes? This is beta, I is a B, or you can call this G and V pi, yes? Okay, there's a formula for G7, and you know R0, right? This it's a 1 over V sub A, I think, no something. Anyway, it's a function of the early voltage. Remember, right? Most of the time we assume the early voltage is infinity, so therefore this one we do not have to include, right? Okay, so that's it. So now you can see that the model has no capacitance at all. And this is what we call the ideal model. Okay, in the real case, you should have some capacitance. So in the real case, C sub pi, R sub pi, C sub mu. Okay. So now you can see it has two capacitors, right? Collector, emitter, base. Okay, and C sub pi is called the forward biased junction capacitance. Okay, and C sub mu is called the reverse biased junction capacitance. And typically these values are given, okay? No. Okay, but that model is difficult to use. So therefore, people have used the Miller theory to try to simplify the model. So C sub mu can be simplified using the Miller theory. Okay, I'm going to skip the details. The details can be found in the book. Okay, so I will just give you the end result. In the end, of course, you have to use some approximations. Okay. Okay, so this is R sub pi, C sub pi. This now is called C sub m, and this is GM v pi or beta id, either one you like. So this is V sub pi, this is I sub b. Okay. So now, the formula for C sub pi, according to the Miller theorem, so C sub pi is equal to, this is important, is equal to, let's see, what's the formula for that? Here's C sub mu times 1 plus V sub O over V sub pi. Okay? I can tell you what is V sub pi, right? Because V sub pi is always equal to I sub b times R sub pi. Yeah? Because when you try to find this, you assume the capacitors are ideal, right? This is open, this is open, right? So V sub pi is always I sub b times R sub pi. But I cannot tell you what is V sub O, because V sub O depends on what? Depends on the circuit you have. This is just the model, you know? You should have something else, right, from the circuit. Okay? So V sub O visible is circuit dependent. Now, just an example. Let's say you have an R surveyor here, right? Then what is C supply? Then, if that's the case, then your V sub will be minus G sub n V sub pi times R sub O in parallel with R sub L, right? Correct? And so therefore, C sub pi is C sub mu 1 plus minus G sub n V pi R O in parallel with R L over V sub pi, which is here. Yeah, but you can just use V sub pi, right? So this pi, V sub pi will cancel. So this becomes C sub mu 1 minus G sub n. Oh, by the way, this is the magnitude. Okay, the magnitude. So let me correct that. So this I just take the magnitude. Okay. So therefore, the minus sign doesn't matter. Okay, so it's 1 plus Gm RO in parallel with R sub L. Okay, that's it. This is 1. What is this? That's C sub pi, right? What is this? C sub n, huh? Huh? Oh, yeah. C sub n. Yeah. C sub pi, again, as I said, C sub pi, C sub mu will be given, right? But C sub n needs to be calculated from this equation. So as I said, I would do an example next time. Then let's go to the model for the MOSFET. Okay.
Quick question.
Yes.
How do you calculate G sub n?
G sub n, there's a formula. Let me see if I can find it.
VT over IDQ.
VP over IDQ, right?
Oh.
Yeah. So you have to calculate the current, the DC current first, and then you can calculate the G sub n. Okay, for the same concept, we can also develop a more realistic model for the MOSFET. Okay, so let me go to the MOSFET model. Okay. G CGDP CGST GNDGS. Right? So that's the model including the internal capacitance. So in the past, these two were neglected, right? So this is called the gate to drain capacitance. This is called the gate to gate to source. Yes. It's the gate to drain capacitance. Yes. And this is VGS. Yes. Okay. Then again, I can use the Miller theory to simplify the model. Okay, so C7 is just the same concept, okay? It's CGDT times 1 plus the magnitude of V small over VGS. And this value will be given, right? And this one will be given as well. So basically, at the end, what you should expect, these two are in parallel, yes? So it becomes a single capacitor, right? Let me call C. And then you can try to find what is the resistance on the left, what is the resistance on the right, yes? R1, R2, correct? Based on the circuit. This is just the model, huh? Then tau associated with this capacitance is 1 over C R1 plus what is it? Parallel. Okay. So omega will be just 1 over tau. Now remember that this is just like the parallel external capacitor, not parallel, right? So therefore, this omega will be in the high frequency range. So let me give you. We have 1 more minute left. So let me say if I have a circuit that has 2 series capacitor, 1 parallel, and plus that, what is the Bode plot look like? Okay, so I have 2 C in series, 1 C in parallel, and these are the external, right? And then you have 1 C internally. Yes? Then at the end, you should expect 2 corner in the low frequency, 2 corner in the high. Yes? So this caused by the capacitor in series. Yes? This is the capacitor in parallel plus the internal capacitor. Yeah? I don't know which one to switch because it depends on the final values. So between here and here, the first drop, you have a plateau. Yes, that's A sub E max. Here, minus 20, right? And then here, minus 40, same. Yes, got it? Okay, see you next time.